Next, we present a few concrete examples of how to calculate confidence intervals for proportions. As we read this problem together, we see that a certain company promises that if you buy one of their products on the internet, they will deliver it to you within 3 business days. Now, realistically, we know that sometimes this will not happen. Problems with personnel, transportation, and even weather might make it so that occasionally deliveries take more than 3 days. We want to get a handle on what the true proportion of packages is that are delivered in 3 days. In a random sample of 200 deliveries, 176 of these were delivered in the 3-day promised period. So let's compute and interpret both a 95 and 99% confidence interval for the true proportion of deliveries made within 3 days. We base everything on our sample proportion of 176 divided by 200, which is 0.88. So in this sample, 88% of the packages were delivered in 3 days. What does this say about deliveries in general? This is just the result from one sample. What can we be 95% confident about? We use the computational formula using the critical value of 1.96, since this is a 95% interval. We substitute the value 0.88 for p hat, 0.12 for q hat, 200 for n, and then we do the math. The margin of error is 0.045, and when this is added and subtracted from 0.8, we get the 95% interval 0.835 to 0.925. The only difference in the computation for the 99% interval is that we use a different critical value. Now the critical value is 2.576. Not surprisingly, the margin of error is larger since our critical value was larger, and the resulting interval is wider. Now it is 0.821 to 0.939. So we can announce that we can be 95% confident that between 83.5% and 92.5% of orders are received within 3 business days. If we wanted to make a statement with more confidence, it would be that we are 99% confident that between 82.1% and 93.9% of all orders are received within 3 business days. Notice the price we pay for more confidence is less precision. The 99% interval is wider and hence less precise. So once again, even though we'd like to be 99% confident of all statements we make, there is the practical reality. As you increase your confidence level, you also increase your margin of error, and your statement is less precise. You have 2 options if your interval is too wide to be useful. You can reduce your confidence level or increase your sample size. For our next example, we'll try to estimate the percent of college students who are only children. To do this, we obtain a random sample of 266 college students and find that 20 are only children. What kind of statement can we make about the percent of college students nationwide that are only children? Let's settle for making a statement we can be 95% confident of. In our sample, 20 out of 226, or 0.0885, or 8.85%, were only children. To compute the 95% interval, it's as simple as substituting in for p hat, q hat, and n into the confidence interval formula. Since the interval is a 95% one, we'll use 1.96 for our critical value. The margin of error becomes 0.037, or 3.7%, indicating that we're able to estimate the true proportion of college students who are only children accurate within 3.7%. So, using this sample data, we can state with 95% certainty that between 5.2% and 12.6% of college students nationwide are only children. One rather exciting aspect of confidence intervals is that they make it possible for us to compare groups. In this example, we have not one but two samples. Our first sample consists of students from public colleges, and our second sample consists of students from private colleges. We are interested in retention rates. That is, how many students who start college go on to graduate. We are not given the actual number of students who went on to graduate, but in this case, the percent. This actually saves us the step of having to calculate p hat. So we see that the retention rate among 505 randomly selected public college students nationwide is 71.9%, whereas the retention rate among randomly selected private college students nationwide is 74.9%. First, we establish a 95% confidence interval for the public college data by using the sample retention rate of 0.719. Next, we establish a 95% confidence interval for the private college data using the sample retention rate of 0.749. I'd like you to take a moment to review the calculations. We can make individual statements about the retention rates of both groups of students, but what might be even more interesting is to compare the results of this confidence interval analysis. I'd like you to think number line. With 95% confidence, we feel that between 68% and 76% of public college students go on to graduate. So we sketch a labeled number line to represent this. To compare it to the private college retention rate, we draw a similar line for the private college confidence interval that extends from 72.4% to 77.4%. And since the 72.4% is smaller than the 76% we sketched on the other number line, we make sure to make it so that these lines overlap. The fact that there is an overlap means that it's possible that the retention rates for public and private college students are the same. Stated differently, we cannot, with 95% confidence, conclude that private college students have a higher retention rate than public college students. The only way we could do that is if the line segments or the confidence intervals did not overlap. Sure, private colleges may have a higher retention rate, but the data we collected in this study does not allow us to state this with 95% confidence. We end with an example where the confidence interval has already been established, and it's our job to interpret the interval and find the margin of error. What we have is a 90% confidence interval based on 50 automobiles that estimates the percent of cars sold in the United States that were manufactured in Japan. Cars like Toyotas and Hondas that were bought here but were made in Japan. I'll give you a moment to decide how you might interpret this interval and compute the margin of error. The interpretation is not difficult. I caution you to be precise and to mention the confidence level, namely 90%, the studied variable, which in this case is the percent of cars made in Japan but sold in the United States, and to convert the decimals to percents. So we are 90% confident that between 29.9% and 46.9% of the cars sold in the United States are made in Japan. You might be a bit frustrated about finding the margin of error. We were given the end result of the confidence interval, not the raw data, so we don't know p-hat. As a result, we cannot use the formula for finding the margin of error. So here is how we'll think about it. How wide is the confidence interval? If we subtract the endpoints, we see that it is 0.17 or 17% wide. If we remember the big idea behind constructing a confidence interval, it is to take our sample p-hat and then add and subtract the margin of error. So we realize that every confidence interval is exactly 2 margin of errors wide. Why exactly 2? Well, we go 1 margin of error below p-hat and 1 margin of error above p-hat. That's 1 on each side, or 2. So it is very important to remember that every confidence interval is 2 margin of errors wide. Our confidence interval was 0.17 units wide. We divide by 2 and find that the margin of error is 0.085 or 8.5%. So the 90% confidence interval we were given allows us to estimate the true percent of cars sold in the United States that were made in Japan accurate within 8.5%. Some people may be disappointed this margin of error is as large as 8.5%. How could we make it smaller? The best way would be to increase the sample size.